Hello, everyone. Welcome to the Analog Electronic Technology course. Earlier, we introduced the fundamentals of feedback and learned how to determine whether a circuit contains feedback. We also clarified that studying feedback involves answering several key questions. Is the feedback derived from the output voltage or the output current? How is the feedback taken out, and how is it fed back? After feedback is applied, does it affect the input voltage or the input current? Answering these questions essentially means identifying the types of feedback, which is what we will focus on in the upcoming sections. In this lesson, we will first study how to distinguish between DC and AC feedback, as well as positive and negative feedback. Let's start with how to identify DC and AC feedback. The classification depends on whether the signal fed back to the input is DC, AC, or a combination of both. If the feedback signal at the input contains only a DC component, it is called DC feedback. If it contains only an AC component, it is AC feedback. If both AC and DC components are present, it is AC-DC feedback. For example, in this circuit, there are clearly two feedback paths, an upper path and a lower path. The upper path is just a wire, so both DC and AC signals can be fed back to the input through it, meaning this path introduces AC-DC feedback. In the lower path, there is a capacitor in series. Since a capacitor blocks DC but passes AC signals, only AC signals can be fed back to the input through this path, which means this feedback path introduces AC feedback. Now let's take a look at this circuit, where we'll focus specifically on the interstage feedback. As shown, this is a three-stage amplifier. It's clear that there are also two interstage feedback paths, an upper path formed by resistors RF1 and RF2, and a lower path involving RE1. The output signal is fed back from the emitter of transistor T3 to the emitter resistor RE1 of T1, thus forming a feedback loop. Since there are no capacitive components in this path, both AC and DC signals can pass through, meaning this is an AC-DC feedback path. In contrast, the upper feedback path includes a capacitor between RF1 and RF2. This capacitor allows the AC feedback signal from the output to go directly to ground, effectively blocking it from reaching the input. As a result, this feedback path introduces only DC feedback. It's important to note that DC feedback serves to stabilize the circuit's quiescent operating point, while AC feedback is used to improve amplifier performance, such as gain, input resistance, output resistance, and bandwidth. Next, let's look at how to determine whether the feedback is positive or negative. One way to judge is by observing the effect of the feedback on the output. In other words, we need to see whether the output quantity XO increases or decreases after feedback is introduced. If the input remains unchanged and the output increases after feedback is introduced, the feedback is positive. Conversely, if the output decreases with the same input, the feedback is negative. Another method is to judge based on the net input of the basic amplifier. That is, we need to see how the net input quantity XID changes after feedback is introduced. If the net input increases after feedback is introduced, it indicates positive feedback. Conversely, if the net input decreases after feedback is introduced, it indicates negative feedback. From the block diagram of this feedback amplifier, we can see that the net input XID is equal to the input signal XM minus the feedback signal XF. So, when the input signal Xi is held constant and is positive, if the feedback signal Xf is also positive, the net input decreases. This corresponds to negative feedback. Conversely, if the feedback signal Xf is negative, the net input increases. This corresponds to positive feedback. Therefore, the polarity of the feedback signal Xf can be used to determine whether the feedback is positive or negative. The polarity of Xf is directly related to the phase shift that occurs during signal transmission, which makes it relatively easy to judge. For this reason, we usually determine whether the feedback is positive or negative by judging the polarity of Xf. This is known as the instantaneous polarity method, which we will discuss next. The procedure of the instantaneous polarity method is as follows. First, assume a certain instantaneous polarity for the input signal and represent it using plus and minus signs. Then, step by step, determine the instantaneous polarities of relevant points throughout the circuit. Finally, evaluate whether the instantaneous polarity of the feedback signal reinforces or opposes the original input signal. If it opposes the input, the feedback is negative. If it reinforces the input, the feedback is positive. In general, the principles for determining signal polarity are as follows. For transistor amplifiers, the polarity at the collector and base, or drain and gate and FETs, is usually opposite, while the polarity at the emitter and base, or source and gate, is typically the same. For integrated operational amplifiers, the output signal polarity is opposite to that of the inverting input, and the same as that of the non-inverting input. After determining the polarity of the feedback signal, we can judge whether the feedback is positive or negative based on that polarity. When the feedback signal and the input signal are applied to the same input terminal of the amplifier, if their instantaneous polarities are the same, the feedback is positive. Conversely, if their instantaneous polarities are opposite, the feedback is negative. When the feedback signal and the original input signal are applied to different input terminals, if their instantaneous polarities are the same, the feedback is negative. If their instantaneous polarities are opposite, the feedback is positive. Let's now look at a few examples. In this circuit, we know that feedback is introduced through resistor R2, which connects the output and input paths. Since there are no capacitors in the circuit, both AC and DC feedback are present. Is this positive feedback or negative feedback? Let's analyze it using the instantaneous polarity method. First, assume that at a certain moment, the input signal Vi has a positive instantaneous polarity. Since Vi is applied to the inverting input of the op-amp, the amplified output voltage VO will have a negative instantaneous polarity. This output is then fed back through resistors R2 and R1 to the node VF, so the instantaneous polarity of the feedback signal is also negative. As a result, the difference between Vi and VF, that is, the net input VID, increases compared to the case without feedback. Therefore, this circuit introduces positive feedback. Let's swap the two input terminals of the op-amp and analyze the circuit again using the instantaneous polarity method. Assume the input signal Vi has a positive instantaneous polarity. Since Vi is now applied to the non-inverting input of the op-amp, the output VO will also have a positive instantaneous polarity. Therefore, the feedback signal VF is also positive. As a result, the net input VID becomes smaller than it would be without feedback. In this case, the feedback is negative. Now let's look at this circuit. It contains both local feedback and interstage feedback. We'll focus on determining whether the overall interstage feedback is positive or negative, using the instantaneous polarity method. Assume that the input signal Vi has a positive instantaneous polarity. Since Vi is applied to the non-inverting input of the first stage op-amp, the output of the first stage is also positive. This output is then fed into the inverting input of the second stage op-amp, so the output of the second stage becomes negative. The feedback signal from the output, which is fed back to the first stage, is therefore negative. As this feedback signal combines with the original input, the net input signal is reduced, indicating negative feedback. Let's look at this last circuit, which we've seen earlier. It's a two-stage amplifier. The first stage is a differential amplifier, and the second stage is a common emitter amplifier. This circuit incorporates interstage feedback, with the feedback path formed by R5 and R6. As we discussed earlier, in transistor amplifiers, the base and collector are out of phase with each other. Assume that the input signal Vi has a positive instantaneous polarity and is applied to the base of transistor T1. Since the output is taken from the collector, the output of the first stage is negative. This signal is then fed into the base of the second stage common emitter amplifier, and again taken from the collector, so the output of the second stage is positive. Therefore, the feedback signal Vf is positive. The net input signal of the differential amplifier equals the difference between the two input signals. Since both input signals are positive, the net input signal decreases, indicating that the circuit introduces interstage negative feedback. In this lesson, we've gained a solid understanding of how to determine AC and DC feedback and positive and negative feedback, as well as their effects on circuits. Let's now summarize what we've learned. First, we introduced AC and DC feedback. The main method to distinguish between these two types is by examining whether the feedback signal at the input is AC, DC, or a combination of both. If the feedback signal contains only AC, it is AC feedback. If it contains only DC, it is DC feedback. If both are present, AC-DC feedback exists simultaneously. DC feedback is primarily used to stabilize the circuit's quiescent operating point, while AC feedback is mainly used to improve amplifier performance, such as gain, input resistance, output resistance, and bandwidth. Then, we introduced positive and negative feedback, mainly using the instantaneous polarity method to distinguish them. First, assume a certain instantaneous polarity for the input signal and represent it using plus or minus signs. Then, step by step, determine the instantaneous polarities of relevant points throughout the circuit. Finally, evaluate whether the instantaneous polarity of the feedback signal reinforces or opposes the original input signal. If the feedback reinforces the input, it is positive feedback. If the feedback opposes the input, it is negative feedback. Therefore, with the input held constant, positive feedback causes the output to increase, effectively increasing the amplifier's gain. Negative feedback causes the output to decrease, effectively reducing the amplifier's gain. That concludes our lesson on determining AC and DC feedback and positive and negative feedback. Thanks for watching.